Hey everyone, and welcome. So, have you ever wondered why a straw in a glass of water looks bent? Or how diamonds get that incredible, brilliant sparkle? Well, it's not magic, it's pure physics. Today, we are diving deep into the fascinating world of light refraction. And trust me, by the end of this, you're going to see the world in a whole new light. Let's get started.
I mean, really think about it for a second. You put a perfectly straight straw into a glass of water, and suddenly it looks like it snapped right at the surface. What is going on there? Is it some kind of optical illusion? Well, yes, it is, but it's not your eyes playing tricks on you. It's a fundamental principle of physics that we are about to decode together.
So this image right here is our central mystery for today. That pencil isn't actually bent. This is a real, physical thing that happens every single time. And the cool part is, by the time we're done here, you'll understand exactly what's happening and you'll even be able to explain it to your friends.
So here's our game plan. First up, we'll uncover the secret behind why light bends in the first place. Then, we'll get into the actual rules that this bending follows. After that, we're going to follow light on a little obstacle course through glass and prisms. Then we'll explore something amazing called the ultimate reflection. And finally, we'll connect it all back to the magic we see in the real world. You ready? Let's do this.
Okay, Section 1, Light's Bending Secret. So, why does the pencil look bent? You know, the simplest answer is that light changes speed when it goes from one thing, like air, into another thing, like water. And when light changes its speed, it almost always has to change its direction too. It has to bend. And this bending has an official name. It's called refraction. It's the change in the direction of light's path when it moves from one transparent medium to another. Now, a medium is really just anything light can travel through: air, water, glass, you name it. It's when light crosses that boundary between two different media that refraction happens. To really get this, we need to talk about two kinds of media: optically rarer and optically denser. It's actually super simple. In a rarer medium, like air, light zips along really fast. In a denser medium, like water or glass, it slows down. Here's an easy way to think about it. Imagine you're running on a paved road. That's a rarer medium. Then you hit a big patch of sand. That's a denser medium. What happens? You slow down immediately. Light does the exact same thing. And we call this slowness factor optical density.
So, what happens when light actually slows down? Let's take a look. Here we have a ray of light going from air, which is rarer, into a block of glass, which is denser. You see that dotted line labeled NM? We call that the normal. It's just an imaginary line that's perfectly perpendicular to the surface. Now here's the first big rule. When light slows down, it bends towards the normal. The angle it comes in at, which we call the angle of incidence I, is bigger than the angle it travels at inside the glass, the angle of refraction R.
So what about the other way around? Well, that's exactly what we see here. Light is now inside the dense glass, trying to get out into the rarer air. It's about to speed up again. And when it speeds up, it does the opposite. It bends away from the normal. So now, the angle of incidence I inside the glass is smaller than the angle of refraction R out in the air. So the two rules are easy to remember. Slow down, bend towards the normal; speed up, bend away from the normal. Simple as that.
All right, that brings us right into our second section. You know, physics is all about finding the rules of the universe, the laws that predict exactly how things will behave. And refraction is no exception. It follows two very specific laws that are basically the rules of this light-bending game.
Okay, here they are, the two laws of refraction. The first one is pretty straightforward. The incoming ray of light, the bent ray, and that normal line all sit on the same flat surface. It's like they're all drawn on a single sheet of paper. Nothing juts out at a weird angle. The second law, well, that's the mathematical secret sauce. It tells us that for any two specific materials, there's a predictable, fixed relationship between the incoming angle and the bent angle. This relationship is always the same, a constant number.
This brilliant little piece of math is so important, it has its own name: Snell's law. It's named after the Dutch scientist Willibert Snell, who figured this all out centuries ago. This simple ratio lets us calculate precisely how much a ray of light is going to bend. It's the formula that's behind everything from designing the perfect camera lens to making fiber optic cables work.
So that constant we keep talking about from Snell's law, that's the refractive index, and we show it with the Greek letter mu. The best way to think about it is as a bending power score for a material. If something has a high refractive index, it has a lot of bending power. It slows light down a ton and really changes its direction. A low refractive index means it doesn't have nearly as much effect.
Here's another way to think about it that might be a little easier. The refractive index is just a ratio. It's the speed of light in a vacuum, which is the absolute fastest anything can travel, divided by the speed of light in whatever substance you're looking at. And since light always slows down when it's not in a vacuum, the refractive index is always going to be a number bigger than 1.
Let's look at a few examples. You can see air is almost exactly 1 because light hardly slows down at all. Water is 1.33, so light slows down a decent amount. Glass is about 1.5, but then look at diamond. It's a massive 2.41. That means light travels more than twice as slow in a diamond as it does in a vacuum. This huge number is a major clue as to why diamonds sparkle so much, and we're definitely coming back to that.
All right, let's move on to section 3. Now that we know the rules, let's actually see them in action. We're going to put light through a couple of little obstacle courses. First, a rectangular glass slab, and then a triangular prism. These simple shapes are going to show us some really cool bending tricks.
First up, the glass slab. As a ray of light comes in from the air, it slows down and bends towards the normal, right? But then on the other side, as it exits the glass and goes back into the air, it speeds up and bends away from the normal. And because the two sides of the glass are perfectly parallel, that second bend exactly cancels out the first bend's change in direction. The end result? The ray of light that comes out is parallel to the ray that went in, it's just been shifted over a bit.
And that little sideways hop has a name. It's called lateral displacement. It's simply the distance between the original path the light was on and the new path it takes after coming out of the slab. And how big that shift is depends on a few things: the thickness of the glass, the angle the light hits at, and of course that bending power score, the refractive index.
But what happens if the surfaces are not parallel? Well, say hello to the prism. Because its sides are angled, the light doesn't just get shifted sideways, it gets completely turned. It bends when it goes in, and then it bends again in the same direction when it comes out. This means the final ray of light is traveling in a totally new direction. It has been permanently deviated from its original path.
And we can measure exactly how much the light got turned. We call it the angle of deviation, shown by the Greek letter delta. All you do is extend the original path forward and the final path backward until they cross. The angle they make is the angle of deviation. It's a direct measurement of how much that prism bent the light off its course.
Okay, get ready because this is probably my favorite part of the whole topic. Section 4, the ultimate reflection. So far, we've only seen light pass through things. But what if it couldn't get out? What if light could actually get trapped inside a denser medium? This is where a really special thing happens, and it's called total internal reflection.
To understand this, we first need to meet something called the critical angle. Now, remember how light bends away from the normal when it's going from a denser to a rarer medium? Well, the critical angle is the one specific angle of incidence that makes the light bend so much that it just skims right along the surface at a perfect 90-degree angle. It's the tipping point, the point of no return.
Let's build this up one step at a time. In case 1, a ray of light hits the boundary between the two media. Its angle of incidence is less than the critical angle, so no problem. It refracts, bends away from the normal, and escapes out into the rare medium. This is just standard issue refraction, business as usual.
Now for case 2, we've increased the angle of incidence until it is exactly equal to the critical angle. And look what happens. The refracted ray doesn't really escape, it bends a full 90 degrees and travels right along the boundary line. We're right on the edge now, so what do you think happens next?
And here it is, case 3. What happens if we just nudge that angle of incidence a tiny bit further, making it greater than the critical angle? Well, the light can't bend any more than 90 degrees. There's literally nowhere for it to go. So it does something incredible. It completely gives up on refraction and instead reflects back into the denser medium. And it's a perfect reflection, as if the surface just turned into a flawless mirror. That is total internal reflection, or TIR for short. No light escapes, it's all trapped.
Now this is super important. TIR doesn't just happen whenever. There are two conditions that absolutely must be met. First, the light has to be trying to go from a denser medium into a rarer one, like from water into air. It will never, ever happen the other way around. And second, the angle that the light hits the boundary with has to be greater than that specific critical angle for those two materials. You meet both conditions, you get perfect total internal reflection.
Okay, this brings us to our last section, where we get to see how all this amazing physics shows up in the world around us. Let's take a look at some real-world light magic. After all, seeing is believing.
Remember our bent pencil from the very beginning? Well, this is the exact same idea.
Have you ever noticed how the bottom of a swimming pool always looks shallower than it actually is? That's because the light coming from the pool floor bends when it leaves the water and enters the air on its way to your eyes. Your brain just assumes light travels in a straight line, so it traces those bent rays back to a point that's higher up than the real bottom. We call this the difference between real depth and apparent depth.
And what about TIR? Is it just a cool trick? Not at all. It's incredibly useful. Things like high-quality binoculars and periscopes don't actually use mirrors to bounce light around. They use specially shaped prisms. Why? Well, even a good mirror gets tarnished and only reflects about 90% of the light. A prism using total internal reflection acts like a perfect mirror. It reflects 100% of the light every time, giving you a much brighter and clearer image. They use these prisms to bend the light path and flip the image right side up.
And finally, the diamond. The reason it sparkles so much is because of that super high refractive index we talked about. This gives it a really small critical angle, only about 24 degrees. This means that almost any light that goes into a properly cut diamond gets trapped inside. It bounces around internally, hitting facet after facet, undergoing total internal reflection over and over again before it can finally find an angle to escape, creating that brilliant flash of light we call sparkle.
Wow, we have covered a lot of ground, so let's do a super quick recap. First, refraction is just the bending of light because it changes speed. Second, Snell's law is the math that tells us exactly how much it bends. Third, a glass slab shifts the light sideways, but a prism actually changes its direction. And finally, total internal reflection is that amazing phenomenon where light gets trapped inside a denser material and acts like a perfect mirror. And there you have it. We've decoded the secret of bending light. So now my question for you is, knowing these rules of refraction and TIR, what other things that you see every day can you explain? Maybe think about why stars twinkle, or why the road seems to shimmer on a really hot day. How does refraction play a part? Drop your ideas in the comments below. Thanks so much for joining me, and as always, keep looking at the world with curious eyes.